All right, welcome back to Étale Homology, everyone. So last time we started discussing the proper base change theorem, which I'm not going to prove, but I'm going to say a little bit about what the sort of key geometric input is. So let me remind you what the statement was first. Well, are there any questions about the proper base change theorem maybe before I start doing that? All right, well, let me remind you then what the statement was. Well, the theorem was that suppose you have pi x to s, which is a proper morphism, and f is a sheaf of abelian groups on the Étale side of x, which is constructible. So let me remind you, what did that mean? It meant that the stalks of f were finite, and that for any closed subscheme of x, there was an open of that subscheme where f was locally constant. Then the theorem was that Ri pi lower star of f, the derived push forwards are constructible for all I, and moreover, we can compute their stalks. So the stalk of Ri pi lower star of f at some geometric point S of the base is isomorphic to the cohomology of the fiber over S with coefficients in f restricted to that fiber. Great, and this is true for all geometric points. S bar and S. All right, so this was what I called the important part of the proper base change theorem. And then there was a corollary, which is that for pi is above, so for pi x to s proper, the formation of Ri pi lower star f for f torsion commutes with base change. All right. So maybe let me make a remark. So Sasha asked, I think Sasha isn't quite here yet, but Sasha asked last time about how to go from the constructible to the torsion case. And I think I said slightly different, something slightly insufficient. So I said it was enough to write f as a direct limit of constructible sheaves, and you can do that sometimes, but I think the right thing to say is that f is a filtered colimit of constructible sheaves for any f torsion, which is not totally trivial. Great, and then at the end of last time, I gave an example to show that some properness was necessary. For example, for constructibility of proper push forward, we talked about the sheaf, the constant sheaf Z mod P on the affine line over a field of characteristic P. Okay, are there any questions about these statements? All right, so doing the proof would be very exhausting, but let me kind of say what the kind of key ideas that go into it. So the key ideas, so first of all, reduce to the case. Sorry, case where pi is a relative curve. So I think it's at least plausible that one can do this. The idea is that so imagine that x was quasi-projective. So at least after blowing up, you can factor pi as a sequence of maps, each of which are relative curves, and then use the Leray special sequence. Well, once you know the push forward through one of those is constructible, then you've reduced yourself to the case of one dimension less. All right. Step 2 is to use dévissage to reduce to the case where f is mu n. So I guess the locally constant sheaf mu n. So this is not so easy. So on a big open, f is locally constant, which means that after passing to a cover, you can make it honestly constant. And then you do some push-pull arguments to reduce to that case. So you get you get a map from f to the push-pull of some constant sheaf, and then that's a direct sum of copies of mu n. All right. Okay, so now now we're in the situation where pi x to s is a relative curve and f is isomorphic to mu n. So in this case, we have a long exact sequence of derived push forwards. So we have 0 to pi star mu n to pi star gm. So here I'm just applying the long exact sequence of derived functors to the short exact to the Kummer sequence. Then we get R1 pi lower star mu n. Then we get R1 pi lower star gm. We get R1 pi lower star gm. And finally, we get R2 pi lower star mu n. Okay, and then it's not totally trivial, but we get 0 after that. So so this is an analog of the so we proved that if the base was a point, so namely if we have a curve over an algebraically closed field, then we have cohomological vanishing in degree at least 2 for the cohomology of Gm. So this is a relative version of that, and it's not totally trivial. One needs to do an analog of what we did earlier over strictly Henselian fields. All right, but suppose we're given this sequence. Well, these groups are pretty understandable. So this is just well, you know how to compute this. If we're taking push forwards through a proper morphism, so this is just the sheafification of I mean, this is just the O cross itself. So this is what we're interested in, and this is what we're interested in here, these two sheaves. So this is not so hard to handle. And so what's the goal? So the goal, so what we actually want to show is that this pi lower star mu n, R1 pi lower star mu n, and R2 pi lower star mu n are represented by quasi-finite X schemes or S schemes. So remember last time we had this criterion that I didn't prove, but I stated for constructibility in terms of representability by a quasi-finite S scheme. So are there any questions about why this is the goal? All right. So okay. So the key. So what's the key geometric input here? It's that so somehow what's happening with this R1 pi lower star mu n and R2 pi lower star mu n can be written in terms of these sheaves, R1 pi lower star Gm, and the key geometric input is that in this situation, so namely where one has a proper curve over a base, R1 pi lower star Gm, which has another name, it's called pic of X over S, is representable by an S scheme, which is locally of finite type. Okay, and one needs a little bit more. One needs a bit of information about the structure theory of this scheme. So this key in geometric input is due to Grothendieck, and it's highly non-trivial. So what is this? Well, in the case that S was spec of a field, this would be the Picard scheme of your curve. Are there any questions about this? So for example, if you have a smooth projective curve over a field, what is this? It's a disjoint union of copies of, well, if you're over an algebraically closed field, at least, it's a disjoint union of copies of the Jacobian, one for each integer.
Okay, and in this situation, so like what are the assumptions we're using here for this fact?
Proper relative curve.
Okay, thanks.
Yeah. So this is really non-trivial. And so maybe it's worth noting, so pick x over s. So what is this functor? So we can actually write it down. So what do we get when we evaluate on t? So we get, what we get are line bundles on the base change of x to t modulo the pullback of line bundles on t on t. And this is not a sheaf, so it's actually the sheafification of this. This is what one gets. So it's really not at all trivial that this is representable. Okay, so once we do this, we basically win though. So once we do this, we get that R1 I lower star mu n is the kernel of this map pick x over s to pick x over s, where this map is just multiplication by n. Okay, and now one needs a bit of structure theory. So in particular, it's not just enough that this is a locally finite type scheme. So for example, you could have an infinite direct sum of copies of Z mod 2, like the constant scheme Z mod 2, and then this, it would not be the case that this kernel is quasi-finite. One actually needs a bit of structure, but and this is complicated by the fact that this Picard scheme does not actually commute with base change in general. Well, sorry, the Picard functor doesn't commute with base change. So yeah, so the key input I should say is the representability and the commutation properties of this with base change, which lets you compute what this looks like by passing to individual fibers and then using what we know about Picard groups of curves. So the claim is that this is quasi-finite, namely that it's actually represented by the scheme theoretic kernel of this map, so the preimage of the zero section under this map. And then moreover that R2 pi lower star mu n, which is going to be the co-kernel of this map, is also quasi-finite. And again, this is non-trivial. So for example, if x over s was a family of smooth proper curves, what this is saying is that this would actually be Z mod n. It would be the co-kernel of multiplication by n on the degree map. So again, this is using structure theory. It's using that the identity component of the scheme is divisible. Are there questions about that? I mean, that was a very, very sketchy argument, I know. So if you have questions, you should ask them. All right, so that's all I'm going to say about the proper base change. If you have questions about it, I'm happy to spend more time on it, maybe in office hours. But let me say a little bit now about how you can actually use it, because I think that's sort of what I want to stress in this course. So now let's just do kind of an example. So let's say we have x to s. Well, let's suppose we have x to s is a smooth proper curve. So let's call this pi, and let's just think about what happens when we compute hi of x étale with coefficients in let's say Z mod n z. So how do you compute this? Can anyone tell me how they would get started thinking about this? Any thoughts? Well, what I would do at least is I would start trying to think about it in terms of the Laurent spectral sequence. So there's a spectral sequence going from HR of S Étale with coefficients in RS, pi lower star, Z mod n. Going to this, and maybe let me replace this I with an R plus S here. So the key question, if you're in this situation, is what is this sheaf? And so what we've just learned about this sheaf is that RS pi lower star Z mod n is constructible. In particular, it's locally constant on a big open of S. And in fact, with a little, we don't know much about constructible sheaves yet, but if you knew a little bit more, what we'd know is, well, we know how to compute the fibers of this. So in fact, we know that the fibers are of RS pi lower star Z mod n Z. Sorry, I shouldn't say fibers. The stalks we know what they are. Because what are they? Well, they're the cohomology, or HS, of XS bar with coefficients in Z mod NZ, which is something we computed. And in particular, the size of this, so the order of this, doesn't depend on S. On S bar, sorry, I'm using S for too many things. So it doesn't depend on the geometric point we chose. So what this is saying is, in fact, once we know a little bit more, we'll be able to see that this is a locally constant sheaf. Okay, and then there are techniques for computing. Let's say if S was a curve, well, I think we probably won't be able to cover it in this class, but there are techniques for computing at least the ranks of the cohomology groups of a locally constant sheaf on a curve. For example, the Grothendieck-Shafraevich formula. So more generally, what if X to S was just a curve? So a proper curve, not necessarily smooth. Well, what we'd know is that the same kind of computation would give us that over the locus in S, so over the locus in S, where, for example, let's suppose that this map, the generic fiber of this map was smooth. So over the locus in S where pi is smooth, we would get a locally constant sheaf. So the R pi lower star Z mod NZ would be locally constant. Okay, so what that says is that over a big open in S, we would be able to hopefully understand these cohomology sheaves, and then we would be able to use techniques we're going to learn later today, so involving cohomology with convex support, for example, to sort of do devisage and get the cohomology over all of S. So in particular today, I want to talk about kind of Gysin sequences and that kind of thing. And so in particular, how do you go from cohomology on an open to cohomology on a big, and cohomology on the complement to cohomology on the union. And so we already talked about that a little bit when we talked about J lower Schriek, but we're going to talk about that more and how to actually compute these objects. Are there any questions about that?
Yeah, I have a question.
Yeah, go ahead.
This seems to suggest that if you have two curves and you can put them in a family together, then, I mean, in a nice way, then their cohomology is the same.
So if you have two curves of the same genus.
Right, same genus, smooth. And
yeah. So that's true, but that we already know, right? We've kind of, I mean, when you say the same, I assume you mean like the same size, the same order, and that we know, right? We've already computed the cohomology of every curve.
But didn't you mention that if we do with Z mod NZ coefficients instead of mu n, then we get an interesting Galois action?
Yeah. Well, we get an interesting Galois action even with mu n. Yeah. So I think maybe what you're asking is, okay, so what about the Galois action? So why is the Galois action the same? So a locally constant sheaf doesn't mean the Galois action is the same on every fiber. Like, in fact, that's kind of not a coherent. I don't think that's like a coherent question, because there's not even an isomorphism between the Galois groups of the residue fields at different points, right? In general, those can be totally different fields.
I see. Okay.
Yeah. So maybe the sort of confusing thing. So the confusing thing is that if you have a locally constant sheaf on some S, the Galois actions on the fibers can kind of vary. Okay, and we've already, I guess you've already seen examples of this. So for example, if you have an elliptic curve over some base, then the end torsion in the elliptic curve is a locally constant sheaf over the base. But as you know, the Galois action on those end torsion points really depends in a genuine way on the elliptic curve.
Okay, awesome. I think that helps a lot. Thanks.
Yeah, great. Yeah, but that's still a locally constant sheaf, and you should convince yourself of that. Great. Yeah. So maybe Arvind, a good exercise would be to actually find a cover that makes that sheaf constant. And this all, by the way, all of this is, maybe I should write everywhere here the characteristic of the base. Sorry, maybe n is invertible on S. Okay, and where did we use that? We used that in this claim where we said, well, these are known, but the statement where we claim that the order of these groups doesn't depend on S, it uses that n is invertible on the base. All right. Were there any questions about that? All right. So now I wanna prove something I owed to you. So proposition. So suppose U is a separated scheme. And F is a torsion sheaf. Let me actually say constructible sheaf. On U, then the compactly supported cohomology of U with coefficients in F. So let me just remind you. So this was defined as the cohomology of X Étale with coefficients in J lower shriek of F, where here J U into X is some compactification. So this is open and X is proper. So the claim is that this group does not depend on X. Okay, so what do I mean by that explicitly? I mean that for two choices of X, so two choices of compactification like this, the groups you get are canonically isomorphic. All right, and we're going to use the proper base change theorem to prove this. Are there any questions before about the statement before I begin the proof? Do you all remember what this HCUF and J lower shriek and so on meant? So the brief reminder is that J lower shriek was extension by zero, and this was the definition of the compactly supported cohomology. Any questions? All right, well, if not, let's prove this. So does anyone have any ideas? I think this is one that we can do together. It's sort of not so hard to deduce it from proper base change. So how would you get started? We wanna prove it's independent of X, which means we need to choose two compactifications. So I'll choose an embedding U into X1, which I'll call J1, and I'll choose J2, U into X2. And what we want is that Hj of Xi with coefficients in Ji lower shriek F is independent of I. So how would you go about this? So how would you produce a map between these two things? Any thoughts? My suggestion would be to dominate them both by a third cover. So how would you produce such a thing? So you want to dominate them both by a third compactification.
Sorry, I'm a little confused by your notation there. It's xi comma j sub I.
Ji lower shriek. So here there's a J1 and a
Oh, is
J2.
that I? Okay.
Yeah, sorry about that. Yeah, it's the I. It looks like a kind of a weird collection of symbols over there. Yeah. So how would you produce a compactification dominating both of these?
Can we embed U to the product of x1 and x2?
Yeah, that's a great idea. So let's take U goes to the product of x1 and x2, just given by J1, J2. And then this projects down to both x1 and x2. So the only problem is that this is not open, this map. So what we're going to do is just set x. I'm just going to set x now to be the closure of the image of J1, J2. So this is inside of x1 cross x2. All right, so what we've done is we've reduced to the following situation. So we have U going into some x, and then x maps down to some x1, where both j's are open embeddings and both x's are proper. All right, now what? And maybe let me call this map from x to x1 pi. So this is one of these projections. So any thoughts? So what we want to do, so we want to compute, we want to compare the cohomology of J lower shriek F on X with the cohomology of J1 lower shriek F on X1. How would you go about that?
Lurie spectral sequence?
Yeah, exactly right. So yeah, so what can we do? We can say, well, there's Lurie spectral sequence, which goes from HR of X1 with coefficients in RS, pi lower star, of J lower shriek of F, and it converges to HR of X with coefficients in J lower shriek of F. Okay, so this is what we want to understand, this thing on the right. And we would like to relate this thing on the left to the cohomology of X1 with coefficients in J1 lower shriek of F. So how would you go about that? So what we want to do is we want to compute these RS pi lower stars of J shriek of F. So can anyone help me do that? So how would you compute what these sheaves are? So let's first try to compute their stalks, maybe. Let's first try to compute the stalks of these things. So let's compute the stalk at some point x bar. So how do we understand the stalks of a sheaf obtained as a derived push forward through a proper morphism? Anyone? So here pi, the main observation is that pi itself is proper because it's a map between proper schemes.
So it's the cohomology of the fiber?
Yeah, exactly right. So it's exactly HS pi inverse of x bar Étale with coefficients in J lower shriek of F. So what is this? Well, there's two possibilities. If x bar is in the image of J, then well, this is just a point. and we're taking the higher cohomology of a point, if X bar is not in the image of J, well then F was 0, right? So in either situation, we get that this is 0 if S is bigger than 0. Right? Do you guys agree with this? So there was a little bit of casework in checking this. One had to look at the situation where X bar was in the image of U and where it was in the complement.
So we're using that it's also quasi-finite, X to X1?
X to X1 is not necessarily quasi-finite. But what it is it's so by construction, it's an isomorphism over the image of U. So what we used is that it's in fact an isomorphism over where and the image of J on the image of J or the image of J1, and then away from that, the sheaf we're interested in has stalks equal to 0.
Oh, I see. That's why you said it's just a point if it's in the image.
Yeah.
Okay. Thanks.
Yeah. So we actually used that about this construction. Yeah. So this uses that maybe I should have written here that uses that these are open embeddings. All right. So what we get then is we actually get an inequality. So this special sequence degenerates immediately, and we get an equality HRX1 with coefficients in pi lower star J shriek F to HR of X J shriek F. All right, and now the claim, which is going to be an exercise, which is that there's a canonical isomorphism between pi lower star J shriek F and J1 shriek F. Okay, and what is the content of this claim? Well, you can, once you construct a map, it's enough to check on stalks, and then again, you can, for example, use the proper base change theorem to check on stalks that the map is an isomorphism. All right. Are there any questions about this?
So I guess the only place that we use a proper base change theorem is that we when we calculate the stock.
That's right. Yeah, but I mean that's somehow the usual way you use the proper base change theorem. Yeah.
All right. Cool.
Yeah, I mean that's the full strength of the hard part of the proper base change theorem. Though that said, like these morphisms are special enough that I think you could honestly probably avoid the full strength of the proper base change theorem. Great. All right, so let's now that we've actually we actually have a definition of compactly supported cohomology, at least for separated schemes of finite type. Let's discuss some of the properties. So here's a proposition. So first of all, first of all, given a short exact sequence, to 0 of constructible sheaves, abelian sheaves, on the Étale site of our separated scheme U, we get a long exact sequence in compactly supported cohomology. All right, and maybe I won't write that out unless there's a request. And second of all, if F is constructible, then the compactly supported cohomology of U with cohomology in F is finite. All right, so let's prove this. So can anyone help me prove the first statement? So maybe let me number these 1 and 2. So can anyone help me prove this first statement? So what do we need to check? So we need to use the definition of compactly supported cohomology, right? Any thoughts? Okay, so what do we want to do? We want along as a sequence, hi minus 1 of x with coefficients in j shriek h to hi x with coefficients in j shriek f to hi x with coefficients in j shriek g, and then so on and so forth.
And those
Right
x's
here.
are U Étales, right?
I'm sorry?
Those x's are U Étales, right?
No. So those x's here, I was about to say, so j is an embedding of u into x with x proper. Right, this was the definition of compactly supported cohomology.
Right.
Yeah, so this is Étale, I guess. So we want along a sequence like this. So what do we need to get that sort of thing? Or what at least would suffice?
If J shriek was exact.
Yeah, and we already proved that last time, I think. So
Yeah.
that was something we checked on Chief. So this arises from the shortest set sequence 0 to j shriek f to j shriek g to j shriek h to 0, which is a short exact sequence because j shriek is exact. And that's something we proved last time by explicitly computing the stalks of j shriek. Namely, they were the stalks of f, g, and h if at a point in u and 0 otherwise, and then checking that implied that the checking exactness on stalks. All right. So that proves 1. What about 2?
Maybe we could show that J lowest shriek of F is constructible on X.
Yeah, that would suffice. So I think we actually already discussed that maybe verbally. So yeah, so the claim is that it's enough to show that J lower shriek F is constructible on X because then hi of x Étale with coefficients in J lower shriek of F is finite by the proper base change theorem. All right, so let's actually check that J lower shriek is constructible. So I think we discussed this a little bit verbally, but it's worth doing. So the claim is that J lower shriek of F is constructible. So we have to check 2 things. So let's check 1, that the stalks are finite. So why is that? So F was assumed to be constructible already, and the stalks of J lower shriek of F are either 0 or the stalks of F. So basically we win because the stalks of F are already finite. So now we have to check that given now we want to check that given T inside of X closed, J lower shriek of F restricted to T is locally constant. On an open of T. So can anyone explain to me why that's true? So you're going to have to use that it was already, this was already true on U, right? Well, so let's intersect T with U. So if that's not empty, then that intersection is an open subset of T, which is closed in U, and thus it has an open subset on which F is locally constant, and so we can use that one. So that's fine. That we win as long as T has non-empty intersection with U. Now, if T has empty intersection with U, then J-Taylor-Shriek F restricted to T is 0, and so we're done. All right. Are there any questions about that argument, which I just gave verbally? All right. If not, then I want to move on. So let me remind you, I kind of discussed the situation where one might use the proper base change up here, theorem up here, where you might like kind of stratify S by looking at loci where isomorphism is smooth, and then try to work on that open, and reduce things about computing cohomology over S to things on the open and things on the complement. So in order to do that, we need a way to relate cohomology on an open to cohomology on a complement to cohomology on the whole thing. And we already talked about that a little bit when we talked about J-Lower-Shriek in the very beginning and sort of introduced cohomology with compact support, but now I want to do that more, excuse me, more systematically. So I want to talk about purity, the Gysin sequence, and cohomology with supports. All right, so first of all, I want to recall some notation that I've used a couple times, but I don't think I've ever introduced officially. So I'm going to let lambda be the constant sheaf Z mod NZ, where here I'm always going to assume n is invertible on whatever base we're working over. So if you'd like, you can think we're over a field, which has characteristic not dividing n. So I'm going to always be working with sheaves of lambda modules. So this means sheaves of lambda modules. Now I'm gonna now as an example of such a thing. So the sheaf mu n is a sheaf of lambda modules. And given a sheaf F, I'm going to denote F twisted by R to be F tensored with the sheaf mu n to the tensor power R. All right, so and this tensoring is over lambda. So over an algebraically closed field, once you choose an nth rooted unity, so once you trivialize this sheaf mu n, this is just isomorphic to F. In general, it's not, and that's manifested in the fact that, for example, the cohomology of F twisted by R will have a different Galois action than the cohomology of F. All right, so are there any questions about this definition and terminology? So this is something that's maybe going to be a little bit disorienting. So we'll see that when we write down Gysin sequences, if you've thought about Gysin sequences in topology, we'll get things that look very similar, but they'll have these sorts of twists showing up, which will tell us that that Galois actions, that the Galois actions are maybe not what you would have naturally expected. And so for example, I mean, this is well, we'll see this in detail, but I mean, somehow there's in topology, when you study Gysin sequences, what you're studying is the cohomology of some sphere bundles, and we'll see the same kind of thing happening here in some more algebraic setting. And what will be the case is that the cohomology of a sphere, or sort of the cohomology of the complement of a point in affine space, maybe, won't have a trivial Galois action. It'll have a genuinely interesting Galois action. And ultimately, that's where these twists will come from. So for example, we already saw the cohomology of Gm with Z mod and Z coefficients is not it has a non-trivial Galois action. All right. Are there any questions about that? All right. Well, if not, so now I want to introduce. So here's a very general way of relating cohomology on an open to cohomology on the complement. And this general technique is called cohomology with supports. So I'm going to define for you a functor. So here, gamma sub z is a functor from sheaves, abelian sheaves on X Étale to abelian groups. And here z inside of X is some closed subscheme. So this is called the global sections supported on Z, or the functor of global sections supported on Z. And the definition is as follows. So it's gamma Z of X dash is defined to be the kernel of the restriction map from the global sections on X to the global sections on U. So okay, so when we evaluate this functor on a sheaf F, what do we get? We get those global sections on X, which vanish when you restrict them to U. So that's why this is called a cohomology supported on Z, or global section supported on Z. And then I'm gonna. So this is so the exercise is that this is a left exact functor. And that's true for the exact same reason that global sections are left exact. And so we're going to make the following definition. So cohomology with supports are the right-derived functors of global sections with supports. All right. Are there any questions about this definition? So hopefully it'll be motivated in a second, but I claim that this is the canonical thing that relates the cohomology of an open U to the cohomology of its complement. All right, so here's the main theorem kind of that I think motivates this definition. So there's a functorial long exact sequence, which goes from the cohomology. Let me make sure I get the indices right. So it goes from cohomology supported on Z to cohomology of X to cohomology on U, and then back to cohomology supported on Z. Okay, and then keeps going. All right, so let's prove this. Well, actually, before proving this, maybe let's take a 2-minute break since we've been going for a while. Does anyone have any questions about where we're heading and what we're doing during our break?
I want to just make sure the coefficients of the sheaf that you want to take.
Yep.
I guess you're starting from the sheaf on the Étale, and then you use the J lower sheaf to go to the X Étale.
So here I'm just working with any abelian sheaf on X, and we'll relate this back to compactly supported cohomology in a bit.
All right.
here-
So all right. So just the pullback. So when you write the U Étale, you just pull back the sheaf.
yeah, you just pull back. That's exactly right.
All right.
Yeah, so this is here. Let me actually write that down. So here dash is a sheaf, an abelian sheaf on the Étale side of X. All right. Are there any other questions about that? All right, yeah, so this isn't totally trivial, actually. I think there's a little bit of an idea here. So let me maybe let me set some notation. So here we have U inside of X. This is an open embedding, and then Z was the closed complement. So what we want to do is we want to reinterpret this. So I don't think this is actually strict. I mean, it's almost formal, but it's not strictly formal from this definition here. One needs a little idea. So what we're going to do is we're going to reinterpret this functor of sections supported at Z in terms of stuff we already understand, namely these J lower shrieks. A couple class periods ago, we introduced this short exact sequence of sheaves. Well, for any abelian sheaf, we had a short exact sequence J lower shriek J upper star of that sheaf, and we're going to apply this to the constant sheaf Z, to the constant sheaf Z, to I lower star, I upper star Z. And we're going to reinterpret this long exact sequence as somehow coming from this one. Does anyone see how to do it? So the claim is that Hom from I lower star, I upper star Z into an abelian sheaf F is isomorphic to global sections with coefficient with supports in Z of X F. Can anyone tell me why this is?
I'm guessing because to give a harm is to like choose one section in the stock over each point.
Yeah, so I think that's somehow the idea. But yeah, let's make it a formal proof. So let's just apply Hom into F to this sequence. So we get Hom I lower star, I upper star, Z into F. So this is what we're trying to understand, to Hom Z into F. So this is just global sections, right? Then into Hom J lower shriek, J upper star, Z into F. Okay, and now here, this is something where you can use adjointness and see that this is just J Hom. So this is Hom J lower star Z, or J upper star Z. Sorry, J upper star F on U, and J upper star Z is just Z. So this is just global sections on U of F restricted to U. All right. So what does that tell us? That tells us that the thing we're interested in, this object, is the kernel of this restriction map, which is exactly our definition of global section supported on Z of F. All right, so that proves the claim. So now can anyone tell me how to deduce the existence of this long stack sequence from the claim? So I claim now there's a sort of a simple construction of this long stack sequence. So we're trying to understand the derived functors of this functor, and we've just interpreted them as this functor as Hom out of I lower star I upper star Z. So is there another way for another name for the derived functors Hom out of I lower star, I upper star Z. So I claim that this claim just implies that HIZ of X Étale F is canonically isomorphic to X die in the category of abelian sheaves I lower star, I upper star, Z F. And why is that? Well, it's because they agree for I equals 0 by what we just proved, and well, derived functors are determined by the thing they're a derived functor of. Okay, and so now what this tells us is that this long exact sequence we want is just the long exact sequence of X's. So namely, we just take Hom out of this short exact sequence, and then the long exact sequence of X's we get is precisely this. All right. Are there any questions about that?
Is there a nice example that we can keep in mind to sort of get a feel for what these should be like?
Yeah, so I'm about to state a theorem, which will kind of tell you what they look like. Yeah, so I mean, this is a very formal thing. I think I think of these cohomology sheaves with support as not really meaning that much. I mean, somehow what they're trying to do is they're trying to compute the cohomology of a punctured neighborhood of Z is how I like to think about it. But they're not, how should I say this? At least to me, they don't seem that geometric until you actually prove a theorem about them. So let me state the theorem, and then we'll see some examples of that in a second. So suppose I have Z inside of X. So here, these are going to be, for now, just K schemes over some field K. And suppose that Z and X are smooth. And so here, you see this is a closed subscheme. So Z and X are smooth, and Z is of pure codimension C. In X. Then the theorem is that for F in abelian sheaves on X Étale, locally constant constructible, so locally constant constructible just means locally constant with finite stalks, then there's a canonical isomorphism between HR minus 2C of Z with coefficients in F twisted by minus C. So let me remind you, so this was twisting by power of mu n, so mu n to the negative C power. So that means take the dual sheaf and take its Cth tensor power. And this goes to this cohomology with supports of X with coefficients in F. Okay, so this is how one computes this. Are there questions about this?
Excuse me, can you repeat what you mean by locally constant constructible?
Yeah, so it just means locally constant with finite stalks.
Thank you.
Yeah, or is the question what locally constant means, or?
No, that's fine.
Okay, oh, cool. Yeah. Yeah, so I actually don't know why. I think the reason people say locally constant constructible is that there's an abbreviation LCC, which is shorter than saying locally constant with finite stalks. So people sometimes will abbreviate this phrase by LCC. All right. Okay, so this I think, I mean, this is sort of what telling you what these things are. the way I think about it is, well, we'll see some examples of this in a second, but or later on, I guess. But let's try an example. So what's your favorite example of a smooth pair like this? So a z inside of x, where z and x are both smooth, and z has codimension, say 1 and x.
Smooth curve in P2.
Okay, that one's too hard because we don't know the cohomology of P2 yet. But maybe we can do like a point in a smooth curve. So maybe let's try z inside of is it just a point inside of A1? So then c equals 1. Oh, by the way, this should be, sorry, this is for all r at least 0. Great. I guess that was maybe clear, but maybe I should write it. So let's take a point inside of A1. So C, we have codimension 1. So we get h r minus 2c. So that's r minus 2 of the point with coefficients in, let's just say, z mod nz. Is isomorphic to hr of the point, supported at the point, with coefficients on A1 with coefficients in z mod nz. Okay, so that tells us what this is. So what is this? This is equal to the following. So it's so maybe let's suppose we're over here, we're over an algebraically closed field of characteristic not dividing n. So then, can anyone tell me what is this thing on the right?
If r is 0, it's just z mod n, and if r is bigger than 0, then it's 0.
Maybe if r is 2?
Ah, you're right.
Yeah. So this is z mod nz if r is 2 and 0 otherwise. All right, let's actually check that this is true. So here we just claimed this, we deduced it from the theorem, but how would you check it? I mean, I claim we can actually prove this without the theorem. So how would you do that? Any thoughts? So we should probably use this long exact sequence we just constructed, right? So we get a long exact sequence, which goes from hi, supported at the point of A1 with coefficients in z mod nz. So this is the thing we're trying to compute, to hi of A1 with coefficients in z mod nz to hi of the complement. So that's Gm with coefficients in z mod nz, and then that goes to hi plus 1 of A1 with coefficients in z mod nz, supported at the point. All right, so can anyone help me out here? What are we getting? So what is the cohomology of A1 with coefficients in z mod nz? Anyone? And so we've computed this, right? So how would you figure this out? And let's not worry about the Gell action. especially because I screwed it up over here. This should be a -1. And this should be a -1. Great. All right. So how would you compute this? So first of all, maybe it would be easier if we did it with mu_n. So how would you do it with mu_n?
Sorry, what does that mean? Z mod NZ with a -1 left?
So that was this thing we defined up here.
Right, but as a group?
So as a group, it's just the same thing, but the Galois action is different. So you're tensoring with Z mod NZ over Z mod NZ, but that the Z mod NZ you're tensoring with has a Galois action.
Okay.
Yeah, so can anyone help me compute the cohomology of the affine line with Z mod NZ coefficients? What's H0? So what are the global sections of the constant sheaf Z mod NZ on a connected variety?
Just Z mod NZ.
Yeah, that's right. So we get Z mod NZ by 0. And I claim it's 0 for I bigger than 0. Why is that? Well, let's just do it with mu_n, and then there's a twist that we get if we do it with Z mod NZ, but let's not worry about it. So there's a Long's sequence coming from the Kummer sequence to mu_n to hi of A1 with coefficients in Gm to hi of A1 with coefficients in Gm to hi plus 1 of A1 with coefficients in Gm. Okay, so what does this look like? So so we get 0 to mu_n to what are the units? What are the global sections of Gm on the affine line? So it's like k adjoin T cross, but what are the units in k adjoin T?
K cross.
Yeah, so this is k cross to k cross. It's the same thing. This is multiplication by n, or n to the power. So we're over an algebraically closed field, so that's surjective. So then we get h1 of A1 with mu_n coefficients to pick of A1 to pick of A1 to, and then everything else is going to be 0. What is pick of A1?
0.
Yeah, exactly right. So this is 0, this is 0, so then this is also 0. Okay, so that's this computation. So we've now computed the cohomology of A1. Let's now compute the cohomology of Gm. Let's do it with mu_n coefficients, just to be simple. So again, there's a Long's sequence, which goes from this to hi of Gm to with coefficients in Gm now, to hi of Gm with coefficients in Gm, to hi plus 1 of Gm with coefficients in mu_n, and so on. And what do we get? So we get 0 to mu_n of k to the units in the global in the ring of functions on Gm, which is kt T inverse, to kt T inverse to h1 of Gm. Sorry, this is a cross with coefficients in mu_n to pick of Gm. What's pick of Gm? What are the line models on the affine line minus the origin? So what happens to the Picard group of a variety when you delete something of codimension 1? So here we're taking the affine line, which had no line models, and then deleting something of codimension 1. Anyone? So I think this is in Hartshorn section 2.6. That might be worth taking a look. So what happens is you quotient by a copy of Z which doesn't necessarily map in injectively. But what that says is that this is a quotient of the Descartes group of the affine line, so it's 0. All right, so what are the units in KT T inverse?
Generated by K star and T.
Yeah, so here we get mu n of k. Here we get k cross times z. So it's really, or times t to the z, if you'd like. Then we get k cross times t to the z. So what's the co-kernel of taking nth powers from k cross times t to the z to itself? Well, that's surjective on k cross because a k cross is algebraically closed, so you just get a z mod nz here. All right, so scrolling back up here, we can look at this short exact sequence. So what happens? So this term, the cohomology of A1, is going to be 0 above degree 0. And that gives you an isomorphism between the cohomology of H1 of Gm and H2 supported at the point. So H1 of Gm, we just computed, was, well, z mod nz with mu n coefficients. So with z mod nz coefficients, it's z mod nz twisted by -1. And that's so that tells us that we get a z mod nz twisted by -1 here, which means in degree 2, we for the cohomology supported at the point, we also get a z mod nz twisted by -1. And that's what we wanted to prove. All right, so in fact, we checked this theorem in this example. And in fact, well, I'll sketch the proof of this theorem next time, but in fact, this example is sort of the base case of an induction argument. And that's why I did it in some detail. So later we'll see why this is true and how to, or at least to some extent, and how to apply it to do actual computations in Étale homology. So next time, for example, I think we'll be able to compute the cohomology of projective space. All right. So we're out of time. Are there any questions? All right. If not, I'm going to stop recording.